Earth, a vibrant planet viewed from the cosmos, gradually narrows to zones thick with industrial smoke, marking our battleground against climate change. The urgency of cutting down atmospheric CO2 levels is paramount in our fight for survival. As our planet faces the urgent challenge of climate change, the quest to reduce atmospheric CO2 has never been more critical. Among the innovative solutions being explored is the concept of direct air capture, DAC, a technology designed to extract CO2 directly from the atmosphere. Thermodynamics sets a firm limit when it comes to scalability and energy. DAC is about fighting entropy. In ambient air, only 1 in every 2,500 particles are CO2 molecules. So, it takes a lot of effort to search through those 2,500 particles to find that particle. Of course, we need to remove more than one molecule. The net result is that we turn a mixed volume of air plus CO2 into 2 separate volumes, one of nearly pure CO2 and the other without. If we remove the barrier between those volumes, the molecules would mix back together in the original disordered mixture. That is entropy. To fight against introit takes energy, and the amount of energy required is dictated by the second law of thermodynamics. In particular, we refer to what is so-called Gibbs Free Energy of mixing. The minimum energy required to separate 1 mole of CO2 at a concentration of 400 parts per million is around 19.4 kilojoule. This is a constraint. If we scale to 1 million tons of CO2, the energy required is around 122.5 gigawatts hour. If we scale to billions of tons of CO2, that is more in line with the amount we need to remove to meet the Paris Agreement. We are talking about billions of kilowatts per hour of energy required. That is insane. Of course, we don't have to try to remove all of that CO2 in just 1 year. We can do this progressively. Let's analyze a few emission scenarios. The first one is RCP85. It represents the most aggressive emission scenario, and business is as usual. Reaching around 520 parts per million by 2050, and eventually racing 2,000 parts per million of CO2 over the coming centuries. A more hopeful scenario is the RCP 4.5, where emissions per year peak around the year 2040. In this scenario, the emissions are reduced, but not fast enough to avoid the 2-degree rise. How much CO2 needs to be removed from the air every year? If we want to reach 450 parts per million by 2050 and start DAC in 2025, then the CO2 removal per year curves look like this. Even in the 4.5 scenario, the peak is 20 gigatons per year, which means billions of tons of CO2 are removed. If the target is reduced from 450 to 350 parts per million, both scenarios will look much worse. The amount of energy needed to capture the CO2 will become considerably high. Considering the status of the DAC technology available and its limitations and constraints, is DAC the only option we have to decrease CO2 levels? From this analysis, it seems the easiest way to reduce costs with DAC is to stop emitting. It is a cliché, but true.